my screen, and can you confirm that you're able to see the Microsoft presentation? It's
Yes, ma'am.
okay. Great. Okay. So you can see the slide which is saying practical research for impactful client solutions, right?
Yes, ma'am.
Yes, ma'am.
Okay. So the agenda for today is going to be, I'm going to talk a little bit about, let me just switch off my dual machine screen. Just give me a minute. Yeah, just share it again. So I'm hearing that the sound is very low. Is that a common concern?
It's audible, ma'am.
It's audible. Okay, so can you please check? Somebody just said in the chat. Okay, I'll continue then. And I'm just going to stop sharing and share again because with the dual screen, it's causing some issues. Okay, so this is better for me. Okay, so I'll talk about, because I lead the AI on Edge practice, I'll just give a brief introduction about it to set the context. I'll talk about, what kind of tech stacks we usually end up working in the practice. I'll also show you one of our unique solution offerings, uh, which we call as visual verifier solutions. And I'll show you some of the use cases that we have developed. What is typically our delivery approach? What kind of challenges and opportunities we encounter? And therefore, what becomes our research focus and what kind of research we have done? And if you want to explore further, then I can even give you some good resources. So basically, Edge AI is basically when we try to deploy, either collect data from IoT devices, such as drones, wearables, mobiles, and either do an on-device inference. So there would be a AI model on that device itself. We try to do inference or a prediction using that data for some business problem on the edge, or we try to collect that data and do an inference on the cloud, but send the result back to that you can say IoT device or edge device. So we can have both the options there. But the point of the fact is that typically the drivers for edge AI solutions are when there is a demand for very low latency, right? We can't transfer a lot of data. So we need to do some computation on the edge device itself, or there is need for a real-time processing where we cannot afford to actually have the delay in going to cloud to retrieve the answer. So we need the device. It could also be a challenge of connectivity, right? You do not have a source through which you can connect to the cloud. It may be an issue because of scaling, because there are too many devices. We really need the computation to happen. It could be a remote location on where you need the basically the device to actually give you the prediction. And secondly, it's more practical and usable. For example, let's say you have some mobile based solution which is mobile, you can take anywhere and do a kind of AI prediction on your mobile itself. So that is definitely much more easy to use. So the usability increases. So these are all the use cases. And in the industry 4.0 scenario, of course, this is all the more, it's a really growing field, right? And the opportunities are that what can we do to improve the compute with the space and power limitations on edge devices? what kind of open source frameworks support edge development better. And of course, as the technology around variables and robots, drones is getting democratized, all these become important. Some of the challenges of the field are because we need there's very limited compute, let's say on a mobile for real time processing. So the models which we deploy on a mobile have to be really quantized and compressed. And then there is also an issue around the limited power which is available in devices of today. There is sizing constraints, memory constraints, and some hardware restrictions. Um, there is also some technology restraints, like we cannot actually train a very robust model on a very small compute, right? So that means you have to collect the data. Either we need to deploy schemes such as federated learning, if you have heard of it, where there are a lot of models trained on different IoT devices or edge servers, and the weights from the trained AI model. So I'm just assuming through the sessions that you've had in the last 2 days, everybody's aware of deep model training and all. So, when a model is trained, we have weights, which is actually uh, holds, which are the parameters of the model. And whenever we need to do an inference, we need to instantiate a model with the same architecture as the training model with those weights using which we can then do the inference, right? So, then we have to work in such a scenario where we can transfer the weights over the network and kind of combine the models trained locally on different servers in a central server. This is what the concept of federated learning is. So we do a lot of work in federated learning as well. And then, of course, practically, actually, because this is a kind of new area, emerging technology, talent is also a constraint. So these are all the constraints under which we operate. And some of the areas in which we work, right? So typically, if you look at the edge platforms and devices, we have different platforms like NVIDIA, Intel, Linux, and then we have our smartphones, Android and iOS based. And for the platforms which are more industrial grade platforms like Linux, Intel, NVIDIA, there are different edge devices or hardware capabilities which come, and they're not very expensive. You can actually purchase them off the shelf, and you can start using these for developing your edge based solutions. What you need to make sure is that whatever models that you train, you may be training on your computer or on a GPU. Ultimately, you need to be able to optimize these trained models, and the uh, size of the models, the depth of our circuits, the network architectures is increasing. So you have like models with billions of parameters now, right? So with whatever you are training, you need to find a way to optimize it. And for this, there are open source libraries like TensorRT, TF-Lite, and OpenVINO for Intel, using which you can actually optimize your models, compress the models, and then deploy them on these small devices. And then once you attach a camera or a acoustics model, acoustic sensor, or maybe a vibration sensor to these, which are giving the data input, and your model is trained, you can make a inference on these devices. So this is basically how we work around deploying different kind of solutions. What I'm going to do today is I'm going to tell you about a very unique offering that we work on, and we own the global product delivery for this. It's called Visual Verifier. And what this really does is, I'll just play a small video for you. So I'll just stop sharing and I'll play the video so that you get an idea of uh, what we do here. So I'm going to share my computer audio, and I hope you'll be able to see that. So just confirming, can you hear the audio? There was music.
Yes, ma'am.
So I'll come back to my presentation. I hope that gave you a glimpse of what we try to do here. So basically, what we have in this technology is we have a partnership with Samsung, and Samsung further on has a partnership with a lens making company called Herman. And what we've done in this partnership is we've designed these kind of small devices which can be attached to the mobile phone. You can see the lens here, the lens instrument. So it can be superimposed on your camera, and this is supported by Samsung S21 onwards mobiles today, and the technology will be commercially available like more. This is not a consumer or B2C technology; it's a B2B technology. So basically, this instrument is available for organizations who are willing to take our solution. Okay. Uh, so now using this, what we do is we have lens which can take microscopic images of material, and we have a mobile app using which we can capture these images and we can connect them to a cloud source. So where you can store the images, then you can do a modeling on the images, and I'll just come to what images are we talking about. And using that, then we can use it on another application which we've designed, which is another mobile application to do an inference or test whatever is our use case. And we are not able to just take images of the solid substances. We can also, like material like cloth or plants or something, we can also do it for liquid. And for liquid materials, what we have is we have a small holder, and we also have some specialized LED lighting instrumentation, which ensures there's going to be an equal distribution of light on the vial in which we hold the liquid. Okay, so the liquid could be something like alcohol, or it could be some liquid chemical. It could be something like oil, wine. So all these
Excuse me, ma'am.
things can be used.
Excuse me, ma'am. Ma'am, can you
Yeah,
please make a full screen?
sorry. Yeah.
Thank you, ma'am.
Okay, so this is how the technology is used, and the different industries that we serve is food manufacturing, textiles, life sciences, in general, any kind of counterfeit products. So, a lot of requirements come to us from retail domain, and then for quality inspections of products. So, this could be again from the food manufacturing or something like, let's say we need a solution for grading the quality of cotton while it is going through the entire manufacturing process. So, we could do a quality inspection. And the good thing is all this technology is available on the go on a mobile. And this is a big problem. So let's say you're visiting an art gallery and you want to, identify the authenticity of paintings in that art gallery based on some signature or some kind of data points that you are aware of. And you can actually take your mobile with you. You can take some images in a certain manner and detect whether the art is forged or not. Okay, using some heuristics which are done usually by human experts, but then we could also uh, ensure that that knowledge is actually captured by the AI model and be able to do that kind of forgery detection. So this is a non-destructive technology. So these were some of the principles of our technology, is that while we are testing a substance or an item, we don't want to destroy it because typically these would be items of value, right? So it's a non-destructive technology. It establishes a confidence threshold because in AI, we always have a probabilistic outcome, right? So it gives us a low confidence, high confidence threshold to take a decision. It gives us results in real time. It is low cost because when we are doing a lot of the quality testing of products, so we are doing, difficult detections. For example, we are trying to, let's say, find out a pill, medicine pill, tablet, let's say, whether it is fake or real. Now, typically, what would happen is you would need to send your materials to a laboratory where there will be specialized equipment, specialized manpower to do such testing, and it will take some time and it will have a cost. So if we can actually have these kind of solutions on the mobile, it makes it low cost. Then we can also automate the process. So quality inspection and production pipelines can get automated. So that saves industries from a lot of labor and cost, money. Okay, so this is the basis of why we are investing in this technology. Some of the proofs of the technology are that we developed the technology, for example, to detect counterfeit paintings, and I just explained that, right? And develop digital fingerprints for paintings. So this is one of the very ancient paintings, and it's called the uh, Yellow Forest. And here it, it is what we are able to do. How we work on this is typically we have an instrument on which the mobile is placed. So there's a mobile here, which is going over a surface of a painting, and at some critical points it takes images, microscopic images of the paintings where there is a very different type of signature in the painting. And then we train a model to identify these from fake and real. And we extract some features from this painting, visual features, using which we can actually develop a signature which can then be compared to find out whether other paintings are fake or not, say from the same painter or from the same era, right? So there could be different criteria in which typically art houses which are doing the auctioning of ancient paintings, they would use such a technology. So we've developed this for one startup client which is into this art gallery and art auctioning. Another example is with a very popular brand of vodka, we were asked to find out whether a particular expensive brand of vodka, can we identify that from any other kind of vodka, or maybe just some alcohol which is mixed with water. So we actually were able to conduct a test based on computer vision using different kind of exploratory analysis in which we could come up with a signature using different color channels of what this original vodka composition is most likely versus that of a competitor, or let's say a non-conformant. Non-conformant would be simply water mixed with some other substance, but still being completely colorless. And that is the good thing, right? All this sample of liquid is actually colorless, and even with that, we were able to extract a signature using which we can segregate from other competitor brands of vodka versus a non-conformant liquid, which would not even have a base of vodka. So we were able to identify a unique signature for it. Some other examples are like we have all these, um, you can say, retailers, big retailers, online retailers who sell their products online. And they have these big warehouses, Amazon, eBay, there are some of the examples. And what they do is at these warehouses, they have this ownership to ensure that fake products are not getting moved on from their warehouses to the distribution centers and then finally to the consumers. And the challenge comes especially with luxury products. Let's say there's a very expensive sample of Nike shoes, for example, Air Jordan. Now, here such a challenge would be that there would be a lot of counterfeits, and the objective is that can you identify the counterfeit um, from the fake product for the same SKU. When I say SKU, it means basically the unit of the product. This is a very challenging problem. Actually, we were working with one of our clients, and the client actually hired an entire company who only had domain experts who could smell a shoe or look at a shoe from different angles, test the leather, etc., to find out whether the shoe is authentic or counterfeit. And especially when the cost of the product goes high, let's say in high-end bags, purses, etc., this becomes very important for them. So this was another sample that we did, and we encountered a lot of challenges, some of which I'll talk to you about. Another example is around edible oil. So everybody uses oil at home for cooking, and when we are using the oil at home, we start wondering that should we reuse the oil after, let's say, frying something, some good snack? Should we reuse the oil or not? And that becomes something in our mind. We use all kind of heuristics. Similarly, to determine whether the oil should be used or not. Similarly, at our let's say in restaurants, oil gets used again and again. In India, by the way, there are no regulations around the oil reuse. So, for example, you'll see the street hawkers and all, they are using oil, they're just refilling oil which is getting consumed, but not ever really changing the oil, which has serious consequences for health. In US and in European nations, usually there's some kind of control. You're not supposed to be using the oil actually. If the number of polar compounds that are getting formed in the oil is above 25%, or if the free fatty acid content in your oil gets more than 5%. So these are some kind of thresholds which are used. And there's no way in which in India, at least I see that we are doing any kind of monitoring on this and there's any kind of control on it. So one of the oil manufacturers actually, which is a US-based oil manufacturer, edible oil manufacturer, told us that they want to find such a solution which they could offer to the restaurants which buy their oil in bulk, wherein they could have a better quality control when they're serving their consumers of products. So there was this food chain, restaurant chain actually, which fries chicken, patties, French fries, all the nice foods that we like to snack on. And they're doing it day in, day out, and they had no way to say when to replace the oil. So we actually designed this mobile-based solution for them. Okay, the process was that whenever the oil, at a regular interval, they used to sample it, send it to a lab, and pay for the lab expenses because it's mandated that they have to get the oil tested regularly. Or there could also be a situation where there is a random sampling by food inspectors who are coming in and testing the quality of oil. And the problem is the results used to take time to come, and there is a complex process of measuring these polar compound and free fatty acid presence in the oil, which takes few hours to give you the results. So ultimately, it would take them 2 or 3 days to actually receive the results. So what we were able to do is again do a visual verifier based solution in which we were able to capture trends of oil quality degradation from day one, from the first frying onwards, till when it is getting degraded and breaching these thresholds. And secondly, we were able to also prove that this works irrespective of the food type that is getting fried in the food, or even if there are multiple foods getting fried in the food. So, for example, uh, whether so chicken has a high protein content, and I'm not sure whether any of you are aware, but in any food which has a high level of protein, the oil deteriorates really fast. It doesn't deteriorate so fast if your food which you're frying is largely based on carbohydrates. So what we try to do is we try to take different varieties of oil, like you can see chicken frying and French frying, and we try to get a signature out from the visual images which we were taking of the oil after filtering it, cooling and filtering, and then fill it in the vial and take a photograph. And we have, of course, applied some research intelligence here to see how can we get the signatures. But ultimately, we were able to achieve a signature by which we can find out whether the oil is going above the threshold or is it still below the threshold, and it can be reused. So what this did was this enabled the company to actually go back to the restaurants, and they were able to either prevent the use of bad oil. In some cases, there were some restaurants which used to throw the oil out daily. So they could actually advise them to reuse. For example, after doing some French frying, they could French fries frying, they could actually reuse the oil once for chicken frying and then discard it. So basically make optimal use of the resource. So these are some of the examples in which we use this technology. However, and how do we actually go and deliver? So why I'm saying this is that this is technology where we need to go back to the industry and we need to give solutions quickly. We can't take like a lot of time to do research. So what we typically do is in 3 months flat, we understand the client's problems. right? It could be of any domain, any kind of material, any kind of objective. It could be quality, it could be counterfeit detection, it could be grading, it could be multiple reasons by which clients would typically come to us and look for us to solve. And we would understand the manual process, like what are they doing today, what are the client problems, and then we would try to come up with a suitable solution for them, deliver a pilot all within 6 weeks, and then do some customization and integration if required into the customer systems, or at least give them a mobile product on their on a mobile which they can download and they can start using. So this is how we go about it. And during this MVP or minimal viable product that we develop for the clients, we may also identify that there are some improvements needed, which will guide us to research further and go back to the client for productionizing this technology. So that is how we typically end up working with them. So within 6 months to 1 year, we can actually deliver a transformational solution which can enable them to, deploy it in real world. So I'll just stop here before I start talking about the challenges and how we went about solving some in these places. Any questions? Okay, so I can't actually see. Let me just stop sharing. So yeah, I can see around 50 people. I just want to understand if there are any questions anybody has. No. Okay.
One question
What's-
regarding that.
Yeah.
Yes, Gaurav, go ahead.
So that regarding that oil thing, when you're saying, is it a US data where companies are going to restaurants and telling them to reuse or throw because, or it's an Indian data?
No, it is a US client, a US oil manufacturer, Gaurav.
Okay. Yeah, that's it.
But I have read that in India too, this regulation is going to come. So actually, we'll have a solution ready
And ma'am,
whenever it
where do
comes.
we get this domain expert like chemistry or chemical engineers analysis on this? Like whether where is the good or bad thing, or does it have a clinical aspect also, like FDA is involved, something like that?
Yes, so FDA may be involved, but more importantly, typically FDA or any other body for that matter would be a governing body. What really happens is, let's say you have a oil manufacturer, what he is supposed to do as part of his own uh, company policy would be that they need to run an R&D lab where they will be having chemists and all. So even when their product is getting manufactured, any edible product has to, abide by certain norms laid down by FDA or whatever the country's body would be. So, so that is why, you know, they most of the companies would have this kind of an R&D center. For example, in pharmaceuticals, there will be a quality control department for the pill production. So we leverage, because we are generalists, our expertise is from the AI domain, right? From software engineering, AI domain, solving the problem, but to understand how the problem is solved in the manual setting. That is something where we rely and involve the domain experts from the client organization. Does
Okay.
that help?
Yes, ma'am. I'm an MTech first year student from IIIT Guwahati, and I'm also a working professional. I work in medical industry.
Okay. Yeah. So I'll show you some examples from the pills as well. Okay. Any other questions? Otherwise, I'll move on. So what I'll be doing now is I'll be showing you some of the challenges while working in Verify. And my intent is to show you that when we work in industry, we come across these new problems, right? And then how do we carve out problems to be solved? And then we get into doing research, right? Which is time bound, where we need to figure out some kind of a solution to solve the business problem. And as a byproduct of that, we do end up creating a lot of assets which can be reused in other problems. So we may come up with some research papers, we may file some patents, we may just, while training my team, for example, I would encourage them to write blogs about the problem. So I'll show you some of those things, what we've done. And that's why I've tried to restrict it on a certain product domain where there is no competing technology today, actually, right? So you can see that using this with the real problems that we encountered, how have we used that to do research in our own company settings, right? As part of client funded engagements, I would say, and solve some of their problems. So let's just move on to the PPT. Okay, so in the visual verification, which I just showed you a few examples of, the key challenges, we have to work with very less data, right? It's not like the open source data sets where you have a lot of data and you can train at your luxury. Typically, in real client situations, we get very little data. Let's say we have a problem of identifying counterfeit versus the authentic. So we will actually, the company who's engaging with us will have very little real counterfeit samples to share with us, right? So we have to work with that very little data and still be able to come up with solutions which can be deployed in real time. And second thing is, when we work in this kind of a data domain where we have real versus counterfeit, or day to day, let's say there's this edible oil, right? Day to day, we need to find out after few hours of frying, how is the quality deteriorating? So you can understand the intra-class distribution between the different samples belonging to different classes is very, very less. So we need very, very sensitive and highly accurate models. And it's not like cats and dogs, or it's not like the ImageNet data set where you have, let's say, very different classes with very strong object features which you need to train on. For us, the problem is that the class distribution is very close to each other between the different classes. So our accuracy needs to be very high on the models. The other problem is we need to go back to our clients and we need to be able to explain to them how are we, how did we actually achieve the outcome and why should they trust the model, right? So how do we explain that is also a high priority area for us, that how do we do this explainability in computer vision domain. Then the other problem we encounter is, let's say we trained on a certain limited data set, right, which had all the kind of products, but when this data will be, when the model will be deployed in real world, then what will happen is it will be tested against all kind of data, maybe data which we had not trained on. What we need to be able to do is identify which data is out of the distribution of the training domain, and hence we cannot predict, or we cannot trust, or we need to have a way to warn that the model has never seen this kind of a sample before, and therefore the human has to take charge, right? So there will be new unknown data in the real world, and is there any way in which we can be very, very smart about identifying this unknown data sample? I can give you another example. Let's say you're doing this shoe counterfeit versus authentic solutioning, right? You're designing a AI model solution for it, and you train on, let's say, 5 different counterpart samples, one coming from Taiwan, from China, from Philippines, and then you have this, let's say, high branded original sneaker, and you have to compare with all 4 of them. So maybe you will pick up one fake which is available easily in the market, and maybe the company is able to offer us this data set. But you never know whether a new counterfeit will come down in the in, let's say, next 6 months. There may be a new counterfeit which has slightly different features, and so we need to be able to find out that, you know, when our algorithm is working, it should be able to flag out that there is a new type of distribution that I am starting to see now. So now we need to study this and we need to figure out how we need to deal with it. So we actually designed a solution for that, and I'll show you a patent around that. And then the other challenge which we have is these are microscopic images. So what happens in microscopic images is we need to look for features. and you'll find that the texture is pretty homogeneous, right? So we need to focus a lot on texture-based identification. Unfortunately, in computer vision, in your CNN models, which we use for computer vision typically, and I'm hoping you have studied a bit about that, what you do is you apply different filters and you do different pooling of those filters to kind of extract the global features from the image. The global features would typically be the edges or the boundaries or uh, changes in the intensity of light and things like that, right? So what happens is when there is a deep uh, convolutional neural network, uh, in the later uh, layers of the network, what really remains are the global features, and we tend to lose a lot of the local features. And then there are, of course, some of the, skip connections and all kind of based of architectures in CNN, using which you can overcome this, but still it doesn't enable us to find out these texture-based features. And I can even show you an example actually here. So let me just share my screen again. Um, Let me go to this paper. So if you can see here, I'm showing you some pictures in this paper. So let me just show you this example, right? So this is a fabric actually. So in this fabric, you'll see there are a lot of images, right? A lot of features which are embedded in the texture, right? So these kind of features, and this is a uh, authentic pair, and this is a counterfeit. What you can see here is a counterfeit, this sample. So these are two authentic samples, and this is the authentic and counterfeit sample, and you can see there is a slight difference. So our networks need to be sensitive enough to find out the differences at this level. And this is not an easy problem even for CNNs, or even more difficult is this particular sample, where there is a authentic counterfeit and this is authentic, right? It's even visually as humans, we are not able to find out the problem with the texture. So this is the ibuprofen tablet actually. And these are the surface of that ibuprofen tablet for which there is one fake sample. So in these kind of problems, what happens is uh, our whole solution has to be very uh, focused on texture based identification. And then, of course, there are some hardware-based improvements. We can make improvement in the sensor technology for the lens, or for even how are we, what kind of resolution should we go with for the images. Then we need very sensitive AI processors. We need good techniques of UX and model compression. So these are the general ones. But the key thing is within the realm of the AI network design, what are the problems that we can do? And this is actually a very open area right now for researching in. So for some of the problems which we have had is, as I told you, one of the problem is that we have very less amount of data. So then the question becomes is, can we do classification using very good amount of data and get an accuracy or not? So the response to this is that classification model does not always work. So in classification, what we do is we take different samples. We would apply a classification model like using mobile net, or uh, using some other kind of simple technique, some standard model, and we would try to give a prediction of authentic versus counterfeit. So this is just an example. It could also be a multi-class classification. But the problem is for training these kind of networks, you need a lot of data. So one approach which could be investigated is, can we use similarity based approach, in which we actually make pairs, like I just showed you. We actually design pairs of data, authentic, and authentic counterfeit together. And we use these to actually compare and train a model in which our loss function changes. And the loss function that we use now is actually a loss function which is called the contrastive loss function. So here what we do is we try to minimize the distance in the loss function. We try to minimize the distance between the Euclidean distance, or it could be any other distance metrics, between two authentic images, and we try to maximize the loss between two images which are of different classes like authentic and counterfeit, with the objective that the network which we are training will learn to discern between the different features in a better manner with less data, and then give a prediction. So this is one similarity based approach that we typically use, especially when we're trying to do counterfeit detection. And there is a complete guide here to the similarity based detection, which I can share with you. So this is a guide which we have actually prepared, and this gives a complete guide to how do you actually go around doing similarity based learning for counterfeit detections, and this is available in public. So what you can see in this guide is we take you through the complete steps of how to go about what is similarity based learning and how do we go about doing it. So this is the example, and I'll just quickly cover this because we'll use it for the same information for one patent. So in the contrastive learning, what we do is we actually take these samples of images, right? And we would pass them through a CNN network, uh, and then take an embedding from the network. So what we do is you remove the last layer which you used before prediction. You extract an embedding, calculate the distance, and then apply a loss function. So this is typically how a CME's network works. And the most important thing is the loss function that we use here. So what we really do in a loss function is we calculate the contrastive loss. We don't do the cross entropy loss. What this really does is for two authentic pairs, we try to minimize the distance, and for two two image pairs which are belonging to different classes, we try to maximize the distance using the loss function. And this is what the loss function looks like, right? So I'll just ask you, are you aware of what this loss function is? Basically, there's a margin, and we try to make sure that the distance between or the difference between the embeddings of two images which are belonging to different classes A and B is maximized, while the distance between uh, two images which are of the same sample are minimized. And we do this by labeling all authentic pairs, giving them a label of 1. And if we are forming an authentic counterfeit pair, we give it a label of 0. So you'll see here that it will be 1 if uh, y is equal to 1, then this should ideally become 0 so that the loss is minimized. Similarly, if y is equal to 0, that means this belongs to the maximum, this belongs to the different pair, right? Because that's how we are labeling our data. So then we would like to minimize this quantity, which means we want to minimize, given some margin, we want to minimize the this distance, this whole factor, which means our distance here should get maximized. So using this as a loss function, we try to make it. And the good part is we can lose, like 1/10 of the data that you actually require for a classification problem when you look at this setting. And the same setting is also used a lot in face detection, for example. So it's a very common algorithm, and it's based on this contrastive loss is actually based on Jan LeCun, who's the director at Meta. He actually gave this paper, so I hope like those working in computer vision, you should be able to relate to this. So what we actually do, coming back to, and there is this entire blog series which takes you into the code using TensorFlow Keras. How can we actually design this, and what are the challenges and how to overcome it? But the fact of the matter is that we develop this kind of a setting to train. This is the first thing. The challenge which we have during this approach is what we found is that the loss function that we have, which is the contrastive loss function, is not sensitive enough for our data, right? Looking at the kind of images. And this is the reason why we had to do some research. And this is actually an output of that research. And it's a paper uh, which we still need to post to archive. we're trying to publish it. But basically what we are doing is we introduced a new loss function. So this is also the extent to which we end up doing research to solve client problems is we have this limited data, we've delivered to the client a model, let's say of 95% accuracy, and our objective is to see with 95% accuracy, we cannot tell them to actually go out in production because they will be missing out on detecting a lot of counterfeits. So what we really need to do is we need to we experimented on how to improve the network, and one of the techniques for improving the network is maybe we need to make our loss function more sensitive. And as I explained to you that the contrastive loss function is actually based on Euclidean distance, and what we were able to do was we did some research and experiments, and we read through some of the papers, papers being the latest research which is out there in in unsupervised learning. So if you look at in unsupervised learning, there's a different challenge, right? We don't have labels, but we need to learn the patterns in the information provided. So we took some inspiration and came up with this uh, new loss function in which instead of just simply taking the, I'll just explain it through a diagram. So when we are taking our entire data through the encoder of the similarity, encoder is nothing but simply a CNN layered network without the rates, without the layers in which we do the complete learning. So basically, these are all CNN layers which are encoding the information from the data. So this could be a batch of authentic. This could be a batch of authentic, counterfeit, whatever. But basically, there are two encoder networks with shared weights, and we are extracting embeddings out of it. And in the contrastive loss function, we understood that what we are doing is we are taking the Euclidean distance. So what we did was we actually introduced, again for comparing both the correlations, we introduced a cross correlation loss. Cross correlation is based on cosine similarity. It's not based on the Euclidean similarity. So we combined both the type of distance functions together to come up with the contrastive correlation loss. And we could also make the architecture flexible. So based on experiments, we using a beta value, which is a hyperparameter, we were able to adjust that how much of Euclidean loss component versus how much of cosine similarity loss component should we introduce into the loss function such to achieve better results for our data sets. And using this, we compared this to the plain simple contrastive loss with our loss function. And what we were able to do is we were able, and these were the kind of samples we tested it around, at least for our research paper. So we took some of our own data sets, which are our client data sets. This data which you see on top, if I just explain this to you, this is actually US defense project where the firefighters have a fabric which is fire resistant, and the objective was that we had to identify counterfeit fire resistant fabric from fire resistant fabric, and we were given a lot of samples. This is just one sample, and our job was to identify whether it is the fire resistant fabric or not, right? Or is it some kind of a fake fire resistant fabric. So this is the example, and as I showed you just a while ago, how we framed it. Another one was ibuprofen tablets. So we were told to identify fake ibuprofen samples which were going out in the market from the original ibuprofen samples by Advil company. This is a company which brand basically. So this was one other one. Another which we just picked in was fake signatures. Okay. So for example, this is a fake signature here. The rest of the three are authentic ones. And another sample which we took was from COVID versus pneumonia machines, just because we wanted to get some public data sets as well in our research so that our research is substantiated. Should we have to justify this for a research paper, right? They would always look to us to see that have we tested our invention against publicly available data, because that's the only thing which a conference or a research body will be able to evaluate against. So we even created some different samples using the MNIST data set where we said, okay, the 9 can look very similar to 4. So we picked up samples where there was a very little differentiation between the original and the fake. Let's say it's like that. Similarly, between 3 and 8. So we picked up these and we created our own data sets of positive, positive, and positive, negative pairs, and we tested our function. And if you look at the results, and so here are our results. So basically, on all the different data sets, we were able to perform much better wherever we had the combined loss function. And especially if you can see here, when the prediction using only the contrastive loss function was low, it immediately improved wherever we could include the uh, contrastive plus correlation loss function. So there we could see definitely an improvement, and we could not see enough improvement on pills, but then we were able to use different methods to get a good accuracy anyway. So in this way, like when we are working in the industry, within a matter of 2 months, we could actually do all these experiments and come up with a new paper, which could enable, of course, help uh, in all use cases, even in our other edge AI resources. But we were able to test it out and prove that this is a better loss function and improved loss function than the contrastive one. So I'll just move back to the presentation. So this was one. So you can come up with new loss functions like this. You can even experiment with changing the different, you can say network architectures. So it was after doing a lot of research on just trying different hyperparameter tuning, trying different network architectures, which we could actually quantize and deploy on a mobile, because our use case is that everything has to get deployed on a mobile ultimately. We were still able to just change the loss function and get much better results. Okay, so with this, I'll move on to also talk about the challenge where we may encounter some new data or some new counterfeit products, for example, completely new data distribution, and how can we deal with it. So before I go on to that example where we have actually filed a patent, is there any other questions just on what I have talked so far? I'll just stop for a minute. I can just check the chat maybe. So Dr. Ravindra Kumar Singh has said, does this also depend on frame rates? So in the examples that I've shared so far, Dr. Ravindra, this does not depend on frame rates because we are taking the static images of the substance. But one use case which we've also worked on is was again based on, I wouldn't say frame rates, but it was based on uh, time. Okay. And that was detection of the growth of bacteria on meat products. So we had this Brazilian client and they gave us this problem that they want to detect that when the meat is getting prepared and it goes through a conveyor belt, and there are various stages of processing and packaging the meat. And their question was that, can you help us in detecting the presence of bacteria on meat? So what we had to do that time was we had to actually take video frames at regular intervals, videos of the meat product. The reason why we had to capture that was because we had to understand at different time intervals was the growth of the bacteria, which has its own incubation time, right? It grows with time. So because of that, we had to actually take a snapshot of videos at regular intervals. And there we had to play around a lot with the frame rates, which are going to be useful enough for us to detect the presence and the growth of bacteria. So we were not looking for dead bacteria, we are looking for growing bacteria, that too on meat products, and that's where we had this challenge of coming up with frames. So typically we took a 5 minutes shoot at, let's say, 5 times a day, and there we were trying to detect the presence and movement of bacteria in frames. So frame rates became important. But by and large, if it's just about a stationary product on which you're looking for features on the, like texture features on the surface, or there's an object which you need to measure, then we don't need to care so much about frame rates. It's just static images that we work with. Shutter speed. No, shutter speed has not been a concern on this. What we do have is we have to focus a lot on the lighting. So in our phone device that we use, we need to make sure the lighting is very uniform. And therefore, the placement of the LED lights with respect to the vial, that becomes important. So we do it in a way where there is an equal light intensity across the entire vial. Similarly, for the object on which we need to place, let's say we have to take a picture of a painting. So what we need to do is when we place our lens, we make sure that it is covering the surface uh, completely, and only the LED lighting is visible. And for that, we actually use our own 3D printed blocks, which we place on the whatever item we need to click a picture for. Because the lighting is most important. That has to be constant and similar, both during the training, data capture, as well as during inference. So that because of lighting, ambient lighting, or the day of the time kind of lighting, there are no impacts on the image. So that becomes the most critical piece in this technology. Any other questions?
Hello, ma'am. Ashish this side. I'm a PhD scholar in MNIT Jaipur. My question is, if we talk about multivariate time series forecasting, then contrastive correlation function, can we use it? Because I have read some paper, I didn't find something that loss functions. So is it will be effective in time series forecasting problem?
So in so the contrastive loss function is useful and it adds value in scenarios where we are looking to compare and contrast, and we want to the network or our model to learn features uh, which help us in learning differences between samples better. So that is the key objective. Now in time series forecasting, our objective is slightly different, Ashish, and I don't think that like you can use this any loss function for that matter. It will learn, but I don't think it will be valuable enough unless you want to measure the change in whatever object you are measuring. It could be text based or it could be vision based, right? Whatever data you're measuring, if you want to find out with time, you are posing your problem in a different way. The way you'll need to pose your problem is you'll need to construct your data also in a different way. You'll have to take data which is you're making pairs of data which are different and which are similar, and then you are forcing the network to compartmentalize the same kind of samples together and the different kind of samples further away in the learned space, right? So that is where the contrastive loss function becomes more relevant. So typically, I have not seen it being used for time series. I'm not sure it will be able to add a lot of value because in time series we pose our data in a different manner. What we try to do is we try to find out the right slices by which we should take the time series and then create our samples, right? So you're really not looking at contrasting two different data samples per se. You want to understand the trends better. So I don't think it will be very relevant there.
Okay, ma'am. Thank you.
Okay, but the other piece which I did tell you is the new data, right? So when we are doing this new data piece, so what are the challenges? So we actually uh, came up with a method and system to detect counterfeit products using semi-supervised similarity-based clustering. So what we really did in this use case was, and I'll go back to the same sample so that it doesn't.
Can you please first? Okay.
Okay. So the challenge again is that what happens is, though we are able to detect on a standard given set our differences, the problem that happens is that we don't have all the counterfeits in the beginning, right? So the way we, as I explained to you, the Siamese neural network is you create two CNNs where you're getting the embeddings of image 1 and image 2, and there is a loss function which could be contrastive loss function. And this is not image 1, image 2. This will actually be the pair of images, similar images and different images. You will train a network. So once this network is trained, you are done. Then what we do is we share any fresh piece of images and we extract the embeddings and do a k-medoids clustering on these images. Now, what is our objective here? Our objective is that I want to design a system in which I can do a clustering based solution of the authentic and the counterfeit. But I also know that in production, when I will deploy my solution, there will be new counterfeits which will come. How will I deal with those new counterfeits? Because they may not either fall close in the cluster of the authentic, nor will they be close to the cluster of the counterfeit, because the counterfeit cluster was formed on the available data distribution I had during the training time. So now this becomes a big problem for us, that if we have to deploy solutions where we train our model, the moment we hit production and there are new counterfeits, it fails to detect it. Like it will give us a low confidence score for authentic and for counterfeit both. And the client will be like in a trouble that what should I do now? My system is failing. In order to solve that, with the intent of solving that, we actually came up with a very unique solution. And this actually came to us from one of our clients who's a big online retailer, and they had this problem with the luxury products which they were actually selling, because every time there was a new counterfeit product coming up in the market and they needed a way in which they could deal with it while leveraging AI for doing the counterfeit detection. So the way this works is, I'll quickly just share with you is, first of all, during training, we take these pairs or triplets of images, pass them to the Siamese network, which we just talked about. We get the embeddings, and then we try to do a k-medoids clustering. So we come up with two clusters, authentic and the counterfeit cluster. And then we apply some thresholding mechanism to come up with a threshold. And the threshold is we try to identify the threshold. And you know, in k-medoids is different from k-means in the sense in k-medoids, we actually try to come up with an actual sample in the cluster as the middle point or the median of the cluster. So that's the only difference. And then we try to also come up with a threshold. So the threshold is nothing but the maximum distance of all the points labeled in a cluster to the center of the cluster. So that kind of a threshold. So we first step in our solution was to identify this threshold, and there's no innovation. This is a very well-known algorithm. But what was innovative was that we used a unique way of coming up with the best clusters. So what we said was we have pre-labeled information, right? Because at the training time, we have been provided with this information of what is authentic and what is counterfeit. So when we pass the embeddings from a trained network, there will be different kind of clusters which can get suggested, and we select the best one given the labels. So wherever the ground truth label is falling in the right cluster for the maximum number of tries, those are the ones which we took as the best formed clusters. So first of all, our accuracy around the cluster identification and selection itself was improved. The second thing that we did was once we got the clusters, that we defined a threshold for each of the cluster, and that threshold was the maximum distance of any sample data point from the center of the cluster. So we got clusters like this for both the counterfeit and the authentic. So once we had the clusters, then we left it at this. During the inference time, you would bring a new image. You will try to, extract the embedding of that new image. Let's say it's a new sample of the shoe. So you'll pass it through your algorithm and you'll get an embedding. And you'll look at that embedding and you'll try to find out whether that embedding is closer to, like within the threshold distance of either cluster. then it becomes easy because you can simply assign it to a counterfeit class or an authentic class. So that becomes okay. But what if this is a new kind of sample and the embedding is not going into either of the clusters, right? So then there could be two scenarios. So we apply a new cluster generation routine to this. So this is where the innovation comes in. So in this new routine, what we do is, if this distance is not equal to any of the thresholds, like not less than any of the thresholds, you can't assign it to a cluster. So we also invented a new global threshold, which was in the entire data set, the maximum distance between the embeddings of any 2 points. We took that as the global cluster. And what we said is, if this new point is falling outside the global cluster, then we will say it is an outlier. If it is an outlier, we will not proceed with clustering and we'll give a warning to a user to go and see what kind of sample it is. Because it could be a sample of another shoe type, which is not even of the same SKU that we ended up comparing against. So we will not consider those points. But let's say it is not belonging to any of the thresholds or any of the clusters, but it is not exceeding the global threshold also. Then the chances are this is a new counterfeit which has come in the market. So there what we would do is we would wait for 2 or 3 points like data samples like this to get collected, and we will then try to form a new cluster. And that way dynamically the algorithm itself is suggesting the generation of new clusters, and there were some integrate steps involved in it. We just filed this patent as well for how to find out the new clusters for out of distribution data. And one step here is also that once you form or suggest the formation of a new cluster based on the few new points coming in your data pipeline which are not belonging to either any of the clusters, which are not even falling outside or they're straightforward outliers, but they're falling still in the distribution, but they're far from any of the thresholds, then we will go and create a new cluster, and the whole algorithm of creating the new cluster and how to find the new cluster center, etc. That is what we try to solve for. And we did this exactly for this e-tailer, where we had a requirement that you need to let us know when the AI thinks that there is a new cluster which should get formed, because maybe it's a new kind of counterfeit which has come. And then it is up to them whether they want to combine and retrain the model to form the cluster again using active learning, or whether we want to just keep creating different clusters for new counterfeit products. That is also a good way, because what happens is then they can analyze, the human experts can analyze the new kind of counterfeits in the market, and accordingly they can give it to the agency which is kind of uh, keeping the track of counterfeit products in the market and all. So this was another patent which we came up with, and this was another novelty, because here we have used clustering and autoencoder, which is the deep model giving us the embeddings of a train network to actually come up with new clusters on the fly, right? So this is another piece that we did. Another kind of problems, like if I just move forward to cover. So this is the new loss thing which we discovered. This was the again the NGC pipeline or new cluster generation pipeline based on k-medoids and autoencoding that we discovered. We went through this. The other problem, as I mentioned at the beginning, was texture-based classification, right? So what I was trying to explain here is typically CNNs are good when we have sharp edges in the image or anything which is like a natural scene. And most of the predominant algorithms and research is always focused on these kind of problems. The other kind of problems could be, you know, like you have to identify the object, you have to either segment the scene. So you need to create different segments of sky versus car versus land versus bicycle, like you have in autonomous driving. The third kind of problems which we usually explain in CNN is around pose detection. So where you draw the skeletal figures and try to understand the motion and different poses. So these are the broad classes, but what is really not a lot of focus on research is how do you identify texture-based classification? So in texture-based classification, if I just try to showcase to you the kind of problems that we have. Let me just show you. So this is another series which you may want to refer to. So yeah, so let me just come to this. So there are a lot of situations in which you don't have clear-cut objects, or you don't have humans, or you don't have natural scenes. But your objective would be typically to find and understand texture from different images. For example, here you can see texture of leaves versus texture of, let's say, some food products, or there could be different patterns that we need to focus on. And this has great number of applications. So here you can see different figures of aluminum foil, different types of cork, wood, even plants. So usually you'll find that when these kind of images are sent into a CNN network, like which we leverage, the transfer learning based CNN networks that we have typically do not work well. And these are three good data sets that are publicly available, using which we did a lot of investigation to see that, okay, what can we do? What improvements can we do to actually address this problem of uh, designing a network architecture, which is very good at doing the pattern recognition on visual images. And what we actually ended up doing was we ended up exploring a lot of these different we ended up exploring a lot of these different methods actually. So, for example, there are classical image processing techniques which focus on texture, and these are well known. So there is local binary pattern wavelet. Wavelet is better on the Fourier transform. So difference between the spatial versus frequency domain of a visual image. So it's based on that fractal image gradient. So these are all different. Image gradient is nothing but studying the gradients in the pixel differences in an image. So these are all the well known. So first we studied all of these and we said, okay, can we use any of them? But the challenge with all of them was these are from uh, the traditional image processing regime. These are fixed algorithms, and there is nothing which we can do to enhance the learnability in these algorithms. So we definitely knew that we wanted to do something in deploying deep learning. So when we started exploring the deep learning regime, so what we uh, were able to come up with is there's a lot of research and there are a lot of good papers again linked here, and I can share the links with you if required. So here we started exploring a lot of these architectures in which within the deep learning network, there are some specialized layers which enable us to extract features which are inspired from those classical algorithms. So for example, how to identify these local features from an image, right? So if you see here, there are actually some features where how uh, the threading of the fabric is working, right? So based on this, there are some certain features which can be extracted. And we started exploring that how do we extract these local features and embed them within the CNN network such that the learning from these features is also aiding in better classification as let's say counterfeit and authentic. So this is what we did, and what we found was there were quite a few, 4 or 5 of these different methods, all based on different encoding layers or based on local binary patterns, based again on fractal analysis. So there are different methods, but there was no one method. What we needed was a generic algorithm. So the more details around this work, which has been researched, you can definitely see here. And we have illustrated very clearly, because I don't have time, I won't be able to go through all of these, but very clearly we've illustrated like how are the different spatial dependencies extracted and presented within the artificial neural network. So So what we wanted was to combine all these methods together. And we have done another work around this, which is, I think, just moving this around, for which we wrote another paper actually. And this we have just submitted. So here what we did was, first we studied and explored all these different papers which I just talked about, but then we did an exploration on different public data sets to find out what is the best design we should have, such that we don't have to apply human intelligence in selecting the best network. So for example, there is a deep 10 feature extraction technique, there is a fractal technique, there's a global average pooling technique. And we had to find out that which are the four best techniques. So for that, we did a lot of extensive experiment where we said that, okay, which technique out of these four works best, maximum amount of time. And then we also said that, okay, if we apply these features, what is the relative feature importance on a generic set where there are all big data set where there are all type of different type of textures coming in. So how can we find the feature importance if we include all these type of different layer formations in our network? So we were able to come up with a different feature importance. So this is the feature importance of techniques in deciding the accuracy. So the way we posed the problem was, we take all these data sets, which I just showed you the pictures of, which are having a variety of different textures. Let's also take all these different research papers which are already out there, which focus on texture extraction from images, and let's combine them, put them all together, and find out that what is the feature importance between all these different deep learning techniques. Once we were able to identify the feature importance was given by which maximizes the accuracy, overall accuracy of the classification. So once we were able to extract this, we actually designed, and because we didn't want to keep trying between all the four methods, what we did was we designed a generic, very generic, this my network. We designed a very generic neural network, which is an ensemble. So here what we have is, we have a proposed architecture, which is, by the way, having less parameters than any one of these methods separately, or even the big CNN models. So this is basically based on an inception network, if you know that in CNN. So it's based on an inception network with some blocks. And here what we've done is, we've built an ensemble of all three techniques, top three techniques in our feature importance. So that is text encoding, that is your fractal FAP, which is a fractal method, and histogram method. So we combined all of them in a single network, and we concatenate the results from all of them before it goes to the fully connected layer and the output. So what this does is, naturally while training, one of these methods for a given data set will be more dominant or better at feature extracting. So naturally the weights of that layer will go up, and the weights of the other two layers may go down. Not necessarily that they will, but what we developed was a technique by which automatically the network is selecting the best features based on the data set and giving us the best output. So by combining, so here in research, what we've done is, we've just leveraged the theoretical research which is available in academia, and we have used that together in our ensemble technique to select the best method, will automatically select the best features and enable us to learn in a better manner. And what we were able to do is, we were able to beat most of the features from the best papers actually. So our ensemble performs better than any of the other papers on most of these data sets. So we're able to achieve all these numbers that you can see here, or we were very close to for some of the data sets. So in this way, by simply applying some of the techniques which we study about every day, like ensemble is a very well-known technique, especially in the classical machine learning. So we applied the same technique in deep learning, to develop an architecture which can naturally work best. So this now is our 2022 results, which are beating most of the results from up till now, whatever has been done around texture classification. So this was another example of the kind of work we end up doing. But using this now, what we are able to do is we are able to suggest to most of our clients solutions which are really unique and which will perform best and solve some of the practical challenges as well. And these are how, so as I said, in the first 3 months, we generally try to identify, experiment and identify most of the problems. And then we plan a different subsequent phase where we actually deliver the solution with some improvements. And it's during this phase that we try to deploy most of our research into production using these kind of methods. So these were the results we just show, and that was really all. I just thought I'd give you some glimpse of um, what all is there. So I'll stop sharing the screen and I'll take any questions.
The session is open for quiz. So the participants are requested to ask your query. And ma'am, there is a query in the chat box by Dr. Ravindra Kumar Singh that do you have any examples on UX?
So user experience is what you mean by UX. So for us, the key thing on user experience when we talk about the verifier projects is the solution which we provide is on a mobile. So we have a mobile app. On the mobile app, we need to have a very quick way of customizing our UI such that it gives meaningful, it interprets the outcome of the AI algorithm meaningfully to the end user. So for example, whatever we detect, let's say the pill surface, right? We need to present a picture of that. And then we need to be able to alter and give a meaningful guidance that what they need to do with that output from the AI model. For example, if it is edible oil, example, then we would suggest to them, that now they should not use it. So we have to add all that interpretation. So that is how we handle the UX side of it, which is pretty. If our model is delivering a good result, that is just a matter of having the conversation that how would the domain experts like to look at the information on the mobile screen and designing a screen in accordance to that. So as far as it is concerned with this, that is really what it is. But if you can elaborate the question, maybe you can speak out exactly what are you looking for on UX. UX on its own is a very broad speciality in software engineering on its own, right? You can talk about user experience design and whatnot.
Well, ma'am, for textual classification, can you use multi-decoder transformer too? Is it really effective?
Multi-decoder. Yeah, you can use a lot of techniques. I just give an example of what can be used. I haven't used it, but yeah, it can be explored. Multi-decoder can also be explored, but I have never used it. See, the key thing that you need to understand, which is different from when we are doing our research projects in academia, is whatever, like if we have to keep in mind the constraints. That will be cost, that will be the compute that will be available on the mobile, because your AI model has to sit on the mobile. We don't do a cloud deployment because these are very sensitive clients. They like to have the AI on the equipment itself. So if you have to deploy your model on the mobile compute, you need to make sure you should be able to compress your model, quantize your model such that it also delivers you the same level or near same level accuracy on a mobile. So that is, those kind of constraints come into picture when we work in actual industry. And that becomes a quite a limiting factor. A lot of things we would not explore because we know it is going to be prohibitive when we deploy the solution in production. So what we try to do is we try to do it different kinds of innovation such that even with a limited computer model is extracting the maximum from the data, and we are able to handle the practical concerns which the client would have.
Okay, ma'am. Thank you.
Okay.
Yeah, ma'am,
Any
there's
other
a,
question?
yes, ma'am, there's a one more participant want to ask a question.
Okay.
Okay. So first of all, good morning, ma'am. This is Sudhanshu Tiwari. I am currently in second year of UG. Okay, so my question is, can we use the AI model to detect whether someone is going to commit a crime or not? As there are several facial expression changes which can be seen by us.
Okay. We can train definitely. There have been um, there has been a lot of work in the area of monitoring for unusual behavior, and also a lot of work around detection of facial expressions, right? But this is a very subjective problem, because uh, at what point in time are you taking uh, the training data? Like, how are you collecting the training data? Like, what is your sample set? So there are not certain expressions. So when you are committing a crime, typically the criminal will try to maintain a very normal facial expression, right? So what are the cues? How are you labeling your data? All those things will come up, right? So it will be very difficult for us to actually frame the problem, is what I believe, right? How will you frame the problem? Secondly, when is the crime getting committed? Is it in day, night? And therefore, whatever data you have collected, the samples that you've collected, what are the environmental factors which are affecting it? And like, I'm not aware of any database per se which can detect. What you can do is you can do facial recognition for known criminals, or for certain kind of, and that is not a completely ethical way of doing it, but based on your how your appearance is, whether you are looking like a certain person from a certain race or locality or culture, you can definitely design those algorithms. But then that all comes with the question of whether that is ethical or not. So the key question for me will be, can we even create a data set where we can extract and label data which is demonstrating, either in a video or in a snip, in very little amount of frames, that these expressions exactly match to the class of crime to be committed. That to me is a very difficult problem. Once you have some unique features, you can train the AI to do anything. But what you don't know is, will, is that reliable? Is the data that you will collect, will that be reliable? So, so that is why I think these kind of use cases are a bit difficult to realize in practical.
Okay, thank you, ma'am. What if we connect the financial statements also in the data and we are having it, then we can just filter the things and about the history of that person. So can we use it?
You can use it. You will just need to make sure a lot on trustworthiness, ethics, where are you getting your data from, and see, you will actually need a very clear data of a set of individuals who have committed crime, who had this kind of a financial background, or whatever other demographics or whatever you want to bring. You will have to create that data set. If you have the data set, you can definitely design any kind of prediction model around it, right? But the point is, will you be able to have a high level of trust on it, right, going forward? So that is the only consideration, because uh, you can always combine a model pipeline, facial recognition or facial expression detection, with some other textual based data. All that is possible. You can have one pipeline which works on different data modalities, even sound. You can say that the way a person is speaking, the way he's speaking, if we know he's going to be aggressive, you can do all that. You can combine it together. But the point is, will it be a practical solution or not? Right? And can you trust and create such a data set? would you have access to all the data to do this? So that is how we need to do it. What I do see a lot of work happening in this sphere is where people are trying to use, let's say, the WebEx or other kind of online methods when people are interacting in a conversation and capturing the videos from there to see whether, let's say, students are attentive during the lecture or not, because that's a very constrained, you can say, focused activity that they're doing. But to create this data set where we are identifying whether a person is committing a crime or not, you need to have realistic data getting captured and then combined, and all of that happening in a very, very ethical manner for us to realize any practical utility out of it. So in bits and pieces, we can do that. Like if you go to airports, right, there are facial detection, which is looking out for the known criminals, but it's just doing a face recognition, right? We can also do something like some suspicious expression, but I don't see that happening anywhere, right? And secondly, there will be a lot of ethical concerns around this, which will have to be addressed before such a such a system can become mainstream.
Thank you, ma'am. There is another query in the chat box of Dr. Ravinder Kumar Singh. Can you suggest any open source or side good in your opinion for computer vision, if possible?
For computer vision in particular, there are a lot of good sites. Just computer vision is what I'm trying to think. So what I usually do is I follow some certain blogs on Medium. Jonathan Hui is a very good author. He writes for everything, but his computer vision blogs are also good. Then I do follow, in general, there are some favorite authors I follow on Medium. And I keep looking at the papers with code for whichever topic is of my interest. So in uh, papers with code is a website where I can identify papers as well as whether they have code or not to go with it. And for any problem of my interest, we can go and look there. And there's another very good site. It's called Connected Papers. So you can put any paper or research topic name in Connected Papers site, and it will search for the paper and all the related papers in latest research. You can identify it will form a bubble graph for you. And then using that, you get in one single click, you can get access to all the research submitted in all the conferences with the ranking, number of citations and everything. And then you can select whatever papers you find of good interest because the abstracts are published and you can go there. So that site I can just quickly share. It's actually, we can just take a look at that. That's a very good site actually. It's called Connected Papers. So this is hosted in Microsoft Azure. So you can just put something like this. Let's say on contrastive learning, for example. If I just put this here, so it will give me all papers related to contrastive, and then I can select any one and it'll create a graph for me, right? Now in this graph, I get all the papers. So from 2015 to 2021, all the research which is available, it will give me that research. And the number of citations is how big the circle is the number of citations. Color shows how recent the paper is. And then I can go and I can select and read the paper. And this is the abstract of the paper. So this way, it becomes very easy to actually search for any kind of papers, and it selects through all resources available online. So this is one good site. And then, yeah, YouTube videos is another good site, depending on whether you have any favorite authors. The Stanford, if you're looking for a course, then I think the Stanford computer vision course is pretty good.
Hello, ma'am. There is another query in chat box from Jayanti Rajiv. Ma'am, how can we develop AI model to identify the fundus diseases? Any suggestion, please?
So what is fundus disease? Is it a plant disease?
If possible, so I request Jayanti Raje to switch on your mic and you can ask the question to ma'am directly.
Ma'am, it is occurring in the retina that is called as fundus. This is any reason technique to develop the AA model? Please suggest.
Okay. So it depends, Jayati, what are the symptoms of this disease, right? So if we get some visual symptoms of this disease, then what we can do is it could be a very good use case for the visual verifier kind of projects, because then what happens if it is changing any kind of coloration, decoloration, or the eye swelling or anything is happening, then we can take the image of this, and we can even design a device by which we can capture an image and give a detection. So this is possible provided there is some visual cue with it. Then you can also uh, put some more uh, data points around it. For example, is the person experiencing fever, like whatever the symptoms are, and on the basis of that we can do it. The work which I have done is on skin diseases. So we were given this challenge to find out if we can identify skin diseases. And what we did was we took these microscopic images of impacted parts of the like skin, and we tried to label 27 different diseases, and this was for skin. So similar, I'm sure something can be done for eye, but what you need to make sure is what is the resolution that you need to click the image with, such that you can identify between it what are the other diseases which also have similar symptoms. We'll have to have some domain expertise where doctors can suggest to us what other diseases may also have the similar symptoms, and then label the sample data that you collect and accordingly design. There may be some good sample data sets already for this disease. You can check that up and do it. But if there are visual symptoms, then you can use a CNN based network for doing it. If there are other symptoms which can be explained using some data set, like whether there's a presence of fever, uh, uh, loss of sight, whatever may be the other symptoms, you can always combine all that data together and design something.
Thank you so much for ma'am for your valuable suggestion.
Thank you, ma'am. Ma'am, there is a one more question. If you talk about industry oriented, for feature selection, there is relevancy, redundancy, and interaction we talk about. So, ma'am, some things are not feasible for the industry point of view. Can you please tell some feature selection that can involve all these three techniques, relevancy, interaction, that is going on in industry point of view?
I didn't completely get the question. Are you saying feature selection, relevancy?
Yes, ma'am. For feature selection, yes.
Okay. So feature selection, one thing which is very important is that in feature selection, what happens is the selection of features depends on the algorithm that you are choosing, right? So if you run different algorithms, let's say you use a forest-based method like random forest or XGBoost, versus if you do something like support vector machines on the same data set, what you will see is the importance of the features of the underlying data, which is same for both the algorithms. It will suggest you different features. And in these kind of situations, what we do is usually we design then these ensemble models so that we can get prediction accuracy from both the models and we can leverage both the models sufficiently. So that is one trend. And another trend, because I work in quantum machine learning, I can tell you is that when we run some of our quantum machine simulators, right? Quantum machine learning simulators, and we use the kind of quantum support vector machines or other kind of algorithms in our data set. They explore the features of the same data set in a completely different manner. So we get very enriched features. In fact, there was one paper from IBM in which we explored financial fraud transactions identification using 67 features And we used both quantum support vector machines and the normal support vector machines, like classical machine learning support vector machines, to improve the accuracy by almost 3% in identification of these financial frauds over a data set of 2.4 million. And that was a lot of data. And that is, so the way you apply the same technique is what is most important, right? So you need to, so for featured importance, I would say is don't stick to one algorithm, try to explore the plethora of algorithms that you can and compare all of them and look at the difference in the predictions. So let's say with support vector machines, there will be some false positives and false negatives. Similarly, with support vector machines, try to analyze which are the ones where the predictions are dissimilar. And what you can also do is you can then train a third model on these kind of false predictions and then put everything in an ensemble and get a very good accuracy. So I would say ensembling is the key thing. And more than feature relevancy, you should also work with the domain experts to find out how you can engineer new meaningful features. So that is also very important. So just as much important is the features which you may be getting, the features which you can engineer is where the difference comes out when we are doing actual solutions for our clients. What differentiates is how smart we can be at engineering new features which will improve the model's accuracy. So these are a few of the ways I would say we should approach feature engineering and feature importance.
Thank you, ma'am.
So all the participants are requested to switch on their cameras so that a snapshot can be taken. Participants are requested to switch on their cameras so that the screenshot can be taken.
Abhishek, bring everyone on the same screen. It should be a square grid.
Yes, ma'am. I'm trying to do that, ma'am.
I hope it was a helpful session.
Yes, ma'am. Definitely, ma'am. Just 1 second. Yeah, thank you so much for all the participants. So thank you so much, ma'am, for a nice session and providing a deep insights on the Edge AI, Edge platforms and devices, mobile verifying technology to check the authenticity of the data. I hope participants would have benefited a lot from this talk. Thanks to all the participants for making this session interactive. Next session will be a hands-on session and will start after lunch at 1:30 p.m. Thank you
Thank you.
so much for joining us. Thank you so much, ma'am.